The purpose of this video is to assess how a matched pairs design experiment can use T procedures to make conclusions about a greater population. Recall that comparative studies are more convincing than single sample investigations. In a matched pairs design, subjects are matched in pairs, and each treatment is either randomly assigned to one subject in each pair, or we might have each subject receive a treatment in some random order. What paired T procedures do is apply our one sample T procedures, which is what we've been working with in class, to the observed differences in these two treatments, regardless of the actual design of the matched pairs experiment. The parameter mu in a paired procedure comes up in a couple different ways. It might be the mean difference in responses of two treatments in a matched pairs design. It might be the mean difference for individuals who have received two treatments, or it might be a kind of before and after assessment of all individuals, what happened after some type of treatment was imposed. Many studies require the use of paired T procedures to involve individuals who are not chosen at random from the population of interest. If you think about this, the most obvious design for a paired experiment is to use identical twins because their genetic makeup is identical, and so we have really restricted the lurking variables at play. This means if we're choosing identical twins, we can't choose people randomly. So that is violated in terms of the selection of our individuals. So think about why we want to randomly select individuals in the first place. For a statistical study, this allows us to generalize the results to a larger population. Since we can't randomly select the individuals, the randomization comes here in terms of the assignment of treatments. So the subjects, if they let us investigate whether or not there is evidence of the treatment effect in terms of who is randomly assigned which treatment, or again, in which order each individual is assigned a treatment. Moving on to just continue the conversation of our T procedures, not just talking about paired procedures, you might hear this terminology that T procedures are robust. Here's what we mean by that. Robust procedures mean that calculations will remain accurate when a condition is not met, and T procedures do that. Using these T procedures, and again, this is for both paired and not paired procedures, the simple random sample really seems to be the most important condition that is met. It's certainly more important for normality, except if we have very small samples that show some skewness. The next three bullets all speak to normality. I'm going to jump to the bottom one here. We know that if n, our sample size, little n, is greater than or equal to 30, regardless of the shape of the distribution, the central limit theorem is going to tell us that the sampling distribution will start to look normal and our calculations using the T procedures will be accurate. I told you that 30 is our benchmark, and now I'm adding kind of a qualifier to it with these other bullet points, and they're actually just going to allow you to use calculations more freely. So if n is less than 15, if we have a small sample, we really want to make sure that our graph is close to symmetric and free of outliers. If we're between 15 and 30, even if you see some skewness, we're going to go ahead and use the procedures and feel comfortable with the results. Only if the skewness is very strong or we see some outliers would we maybe not want to use the T procedures if our n value is between 15 and 30. To bounce back to the paired T procedures, I just want to show you an example, one of the problems from your book, problem 1041. This is where we might use this concept of paired procedures. So, the National Endowment for Humanities sponsors summer institutes to improve the skills of high school language teachers. We've got 20 Spanish teachers who work for 4 weeks. At the beginning of the period, the teachers took a listening test to see how well they understood spoken Spanish, and then after 4 weeks, they took the test again. The table below gives us the pre-test and post-test scores. The maximum score is 36. We want to construct and interpret a 90% confidence interval for the mean increase in listening score. So I want to direct your attention over to my messy writing here. In list 1, I'm going to enter my pre-test scores. So that's everything in this second column and in this second to last column. Notice that the column for subject is really just numbering the individuals. Those could be names and it would have no impact on our data. So I put pre-test scores in L1. I put post-test scores, so the third and sixth columns, in L2. And I used L3 to subtract them, post-test minus pre-test, in order to find their difference. Because as it says, we want to construct and interpret an interval for the mean increase in listening score. So this is running under the assumption that the post-test is going to be higher. So, following the same 4 steps we've used previously, we're going to state our population and parameter. So we're looking at Spanish teachers. Our parameter of interest is the mean increase on the listening score. In terms of our conditions, we certainly can't think about these individuals as a simple random sample. It doesn't say they were randomly selected to go to this workshop. Teachers who choose to go to a workshop in the summer might be going for various reasons. That doesn't really allow us to conclude that there's randomization. So we're going to proceed with caution, even though random sample is kind of the most important condition to us. I just want to show you how the calculations would work if we did have that random sample. In terms of normality, I am looking at a box plot on L3. I want to look at what the differences show me, since that's what I'm going to construct my interval on. And if you're doing this with me, you should get something that looks slightly skewed, but certainly not strongly skewed, no outliers. N equals 20, so we're not quite to that 30 benchmark, but no strong skewness, so we feel good about it. We know that there are more than 200 Spanish teachers in the world that we're pulling from here, so we don't need to worry about independence. For my calculations, notice that I'm not given anything in the bulk of the problem except really the N value, which I could have taken from the table as it is. I have to run my 1-bar stats on L3 again in order to get my X bar, in order to get my standard deviation. I have 19 degrees of freedom. We are told we want a confidence level of 90%, and so the appropriate T-star value is 1.729 using your T-distribution table. So use that to do your calculations. Plug them in and interpret your results. So we're 90% confident that the mean increase on listening score for all Spanish teachers is between 0.21 and 2.69 after attending the Institute. So just based on the numbers alone, it looks like there is an improvement. It doesn't look like there's a huge improvement, but there's an improvement nonetheless. The very last part of this question asks if you can conclude that attending the Institute causes Spanish teachers to improve their listening skills. And we should not determine cause and effect here for a couple of reasons. One, we don't know that these teachers were randomly selected. And two, we would need to conduct a randomized experiment in order to be sure about the cause and effect. There isn't a control group here. We haven't compared a group of teachers who weren't going to the Institute to see whether or not their listening skills just improved with a lurking variable of time in the background. So still leery of our results for a couple different reasons, but this is how those paired procedures work in general.